Welcome to the Physics Fun Demo Show, everyone. My name is Larry Weinstein in the Physics Department at Old Dominion University. This is my lovely assistant, Perry Nerem, and we'll be demonstrating some of the wonders of physics for you over the next few minutes. So what I want to start with is the seat of nails. This seat has several hundred sharp nails on it, and, well, you know, people will tell you that you need to be getting that really spiritual frame of mind in order to sit on a seat of nails. But it's actually really just physics. You just sit down, there you are, and you're just fine. Now, what I like to say when I invite people up to try the seat of nails is I ask them, have you sat on a seat of nails before? Most people will say no. And I'll say, try the starter seat. It only has one nail. That gets the point across, because with 300 nails, it spreads the force out over all 300, and I can sit on it just fine. Speaking of pressure, the next thing that I want to look at is water pressure. So what I have here is a pan balance, and it's balanced. I've got mostly balanced. There's a beaker of water on one side, there's weights on the other, and you know, if I put a little force down here, that goes down. If I put a little force here, that goes down. The question is, and think about it before I do it, if I put my finger in the water without touching the sides or the bottom, what's going to happen? This side can rise up, it can stay the same, or it can go down. Think for a couple seconds. Here we go. So I put my finger in the water without touching the sides, and it made this side heavier. How'd that happen? Well, my finger's pushing down in the water, my water's pushing up on my finger, so my finger's pushing down on the water, so it's adding force to this side, and it gets heavier. So the question is, what happens if I put a piece of cardboard over this cup and turn it upside down? So here we go, piece of cardboard, uncupped. Oh, it doesn't stay. But if I fill the cup with water, and then I flip it over, then, oh, wait a minute, the cardboard's staying. How'd that happen? Well, right now there's lots of water inside, but there's air pressure, and air pushes really hard. There's a vacuum up top, so we've got some water pushing down, all the air here pushing up. If I can let air into the inside, then it lets go. So on the nature of how hard does air push, we want to take a look at how hard air pushes. So here we have an empty sphere, nothing inside. Well, that's not quite true. There's air inside. And so if we can in fact replace the air with nothing, with a vacuum pump, and that's what we're doing now, is we're sucking the air out, turning on the vacuum pump. Here we go. Pulling out the air. Now I'm going to close this valve, and we'll turn off the pump, disconnect it, and now it doesn't come apart. And in fact, we can pull really hard, and it's not going to come apart until, watch out now, I open the valve, let air back in. So if I've got air inside pushing out and air outside pushing in, it's really easy to pull apart. If there's air outside pushing in, nothing inside pushing out, then we can't pull it apart. So let's take a look at this with a soda can, because that thing's made of steel. It's pretty strong. We're going to do it with a soda can, which is not very strong. So let's see what happens. So the first thing I need to do is to light my propane torch. Now I'm going to take just a standard empty soda can and put in a little bit of water. Not too much. Not even an ounce. I'm going to take a sophisticated vacuum valve. This is called a piece of cardboard. Put it over the top, just to block the path of it. Then I'm going to heat it up. I'm going to put it in the propane, and the propane is going to make the water boil. When water boils, it takes 1,000 times more volume, and now I've got air on the outside pushing in, I've got air on the inside pushing out. I've got air on the outside pushing in, I've got water vapor on the inside pushing out. You can see it's boiling furiously. If I can get rid of that water vapor, then the can crushes. Because once I dunk this can in the water, all the water vapor that was inside condensed. I had air on the outside pushing in, nothing on the inside pushing out, and the can went crunch.
All right, so continuing with this idea of what can we do when we heat things up, I've got two balloons here. One's just filled with air, and one's got a little bit of water in it. See if you can hear that. All right, what I'm gonna do is heat them up. Take my candle. All right. Bring my balloon in nice and close, and see what happens as the rubber in the balloon starts to heat up. Suddenly it pops. Right. So let's try that again. Let's use the water balloon. So this time, right? Same type of material, but it's got a little bit of water in there. Bring it towards that flame. What's going to happen here? Am I going to make a big splash? Nothing's happening. Why is that? Yes, with the previous balloon, the candle was able to heat up the plastic, melt it a little bit, cause it to pop. But here, there's that water that's inside the balloon. And so we're heating up the water as well, preventing the rubber from reaching that critical limit where it suddenly fails and pops. So we've got a camera aimed at me so that you can see how I'm glowing in the infrared spectrum. You can see different objects on me, like I've got a pocket protector here. Nice and cold. Go to my exposed skin, nice and warm. So let's see what kind of thermal objects we can play with here. I take myself in view. Got myself some cups of ice. Let's aim at that thing, right? So I've got cups of ice. You see how they're that nice dark color in the camera? It's because of how cold this is. The temperature setting is scaling these away. Now if I switch to something like nice thermostat, warm water, you can see down here in the cooler region, right? This thermostat is trying to keep the hot water that's inside the cup contained. But you notice up here, see how it's a little bit warmer? Because that water is escaping, right? Should be good and pour. There we go. Right. As I pour that hot water, you can see that wonderful temperature changing, moving around the cup. Throw some ice in there, start melting it. What are the other things we can do with this camera? We can talk about how visible an object is to the infrared spectrum. Because the camera that you're seeing me at right now is looking at the visible spectrum. And I've got a black bag here. If I was to stand in front of the bag, you wouldn't see my face. But I look at the infrared camera, take that black bag, and you still see my face. Try and wiggle my eyebrows if you can see that. Right. So even though on camera, in the visible spectrum, this bag looks opaque. It looks like you can't see it. To the infrared, the rays go right through. What about this? Got myself a nice piece of glass. On that camera, you can see me nice and easy. Bring it over here. And I've blocked myself out. Take out my heart, right? Go back to my face, right? So here's material. Here's an example of something where in the visible spectrum, right, the light's able to transmit through, yet something in the infrared, the temperature we tend to associate with warm, hot objects, it's completely opaque, completely blocks out. Try writing messages on this. We've all heard this idea that warm air rises, and so what we have here is a strange type of beaker. It's filled with liquid. I'm just going to put a little green dye in there, give it some color. Right. So you can see that the liquid is pretty stationary. What I'm going to do now is introduce some convection. I'm going to heat up this corner here. Right. We'll try and just get this corner here nice and warm. And we'll start to see how as the water gets hotter here, let's get that a little bit closer. We're going to start to create a flow. You can see how the currents are being generated here. That warm air, in this case though, warm liquid, is being pushed up into a less dense region of the tube. As it rises, it tends to cool off, come back here, start to fall. And now we've created this convection, right? We've created this cycle of the warm material rising up and flowing things around in this circle. All right. We've almost completed our first loop. And we can keep this going on. Take the heat away. You can start to see where the warmest regions is as it's trying to convect around, flow. Let's get me out of the way.
Okay, so the next thing that we want to look at, Perry, if you would take this away, please, is we want to look, since we started looking at moving fluids, we want to look at what happens when the fluid, which can be a liquid or a gas, moves quickly. So for this, I'm going to take off my mask. And the question is, what happens when air moves quickly? Well, there's an easy demo I can do. I can just blow over the top of a piece of paper. And if I do that, you think, well, gee, the air's rushing out, it's going to push the paper down. It doesn't. The paper rises up when I blow on the top side. And that's because a moving fluid actually has less sideways pressure than a non-moving fluid. And this is part of the reason why airplanes fly. It's a bit more complicated, but this Bernoulli effect is part of that. And we can see that with something else, where I'm going to take this blower to give me a current of air. This blower is blowing air straight up, and I can suspend this ball in the current of air. Now, that's not terribly surprising, because the air is pushing up, gravity is pulling down, but I can also tilt it a bit, and it's staying in the airflow. That is weird. Now, if I tilt it too far, it falls out, but it's staying in that airflow, and it's stable, because the air going up, it's fastest in the middle of the flow, there's the least pressure, and the ball stays where the pressure is the least. I can demonstrate this another way. I have here a complicated scientific device where when I blow into it, I make a current of air going up, and the eyeballs stay suspended. The last way I can do this is I have a funnel and a ping pong ball. And if I put the ping pong ball in the funnel, it's not going to stay there. But if I can blow through the funnel, wait a minute, you're thinking he's blowing down and it's going to make the ball stay up? How does that work? Well, like this. As long as I'm blowing, That ping pong ball is staying up, and the reason for that is that the fast-moving air has a lot less sideways pressure than the regular air. There's less pressure up here where the air is moving really fast, more pressure from below. The ping pong ball stays up. That's called the Bernoulli effect. We can see another couple examples of what that does. So, take it away, Perry.
I've got here what we call an air cannon, right? Just a little spring-like area. I'm going to spray some smoke in here, or just a can of smoke, and start seeing what happens when we have some flowing air. So let's fill that up for a bit right now. Just get a nice, decent amount of smoke up into this thing. Keep going for a little bit longer. Let's start there. We'll try and go across the camera. Get ourselves these wonderful smoke rings. Do one shot at the camera. And you can see that you get this actual ring shape of the moving smoke cloud due to the cut off of the shape here. So, another one we can do. Start applying Bernoulli's principle. All right. We talked about how I can reduce the pressure in a region. So what I'm going to do is use my can of air, my air cannon, to knock these things down. So let's get my aim right. I'm aiming right between the two. What happens when I hit? They moved in. We'll set that up one more time, but a little bit more space between them. All right. So I'm not aiming at a cannon. I'm not trying to knock one down. I'm going in between and seeing what happens to those soda balls when that rush of air flies by, reducing the local pressure. That flowing air, when that air is in motion, the pressure around it is reduced. So some other things we can do with this. All right, we're trying to exploit the objects moving in air. Right? Has anyone ever thrown a curveball? What's the trick? You take your baseball and you gotta give it a good spin. Well, I'm gonna cheat. I have myself here, a nice little thrower here, got some sandpaper in it. That allows me to grip this really well and give this ball a nice, great spin. Let's get this camera out of my way. What I'm gonna do is try to give it a spin. I'm gonna throw it straight like that. Watch the curve of the ball. So notice the curvature of the ball. That rotation is changing the air pressure around it. So we'll try to throw at the camera, and I'm going to curve it sideways. Just again. So I'm throwing at the camera, and we see the curve. One more. And we see the curve caused by that rotating object to cause it to arc in the air.
Okay, so we've been looking at heat, we've been looking at moving air. Let's go back to heat and take a look and see what materials do. We already said when we heat water, it expands, it becomes less dense, it rises. And we saw that with the convection. Here what I've got is I've got a plate, I've got a ball. The ball does not fit through the plate. So the question is, what happens when I heat up the plate? When I heat up that aluminum plate, aluminum is going to expand. So here's my aluminum plate. I'm heating it up. When the aluminum expands, is the whole inside going to get bigger or smaller? So I'm heating this up, and am I going to be able to get the ball through the hole in the plate once I've heated this up? So it'll take me a few more seconds to heat it up. I've got a lot of aluminum here. It's a fairly thin plate, but it's fairly large. And so we've heated up the aluminum plate. And when the plate gets bigger, the hole gets bigger too. Huh, interesting. So what happens is that when the aluminum plate expands, it's kind of like blowing it up on a Xerox machine. The outside gets bigger. Yeah, I touched it, I'm an idiot. The outside gets bigger, it's hot. The inside also gets bigger, the whole thing gets bigger proportionately. Now, the other thing we've looked at before is we've looked at air pressure. And what we've said is that, great, thank you, air pushes really hard. And so what I've got here is a thing called a vacuum cannon. Here's my projectile. It's a ping pong ball. I'm going to drop it down. There's nothing inside this. This is just an empty PVC pipe. I've got an inlet here so I can use a vacuum pump and suck the air out. I've got a piece of aluminum foil on the end. That's my vacuum seal. Not very strong, you're thinking. You're right. And on this end, I've got the top of a soda can, and I'm placing it on. And now this is reasonably airtight. So I'm going to take the vacuum pump, plug this in, and before you turn it on, we're going to pump it down, and then the aluminum foil is going to rupture. That ping pong ball is going to come flying out. You'll hear that impact. Go ahead and turn it on. So here we go. And the ping pong ball shot out, hit the wall, bounced over there. The first time I did this, I did it in a middle school auditorium with a racquetball. The racquetball hit the far end of the auditorium with such an audible thwack. I was grateful I hadn't hit any of the students. That could have been interesting. So, we've now looked at what happens with pressure, that air pushes really hard. We've looked at temperature, that heat makes things expand. We've looked at water, that water can absorb a whole lot of heat. The next thing we're going to do is we're going to look at extremes of cold. So now what we're going to do is we're going to look at the properties of liquid nitrogen. And nitrogen's in the air all around us, but the question is, what happens when we make it a liquid? Take it away, Perry.
All right. As usual for safety, I'm going to use gloves because we're dealing with some pretty chilly stuff. All right. Take my little dewar here. I'm just going to pour it out right now. Pour it into this display dewar here. Oh. Watch it fill up. Oop. You're seeing a mixture of the liquid going into the dewar and all this fog around it. Now fog is mostly water molecules in the air condensing down. Probably a good amount. Put that on the side. All right. Thank you. So let's take a little ladle, scoop some of that stuff out. Try and convince you it's a liquid. And we'll just dump it on the floor, on the tabletop here. You see it instantly evaporating. This stuff is so cold. It's so cold that in our room temperature, it's basically boiling. So we got this constant boiling material as we're flowing around. So let's get some into a nice clear cup. Probably easier just pour it in. Come on. There we go. So you can see how it's constantly, it looks like it's water that's boiling, but that's this liquid nitrogen just constantly evaporating in this area around us. Nice clear substance. You can see as I put it down, it touches that warm table, it starts boiling over and over.
So Perry's been referring to this as really cold, but the question is it cold or hot? I've got a tea kettle. Now, when tea kettles whistle, it's because they're really hot, right? You put a tea kettle on the stove, you put water in the tea kettle, and what happens is that when it gets really hot, it whistles. So the tea kettle is whistling, thus it must be really hot. Well, what's happening is the liquid nitrogen for us is really cold. But because nitrogen boils at a very low temperature, to the nitrogen in the tea kettle, the surroundings are really hot and the nitrogen is boiling away. So just to show you what it looks like, we have a thermometer here, and we're going to take a look at what our temperatures are. So here we are. This is sort of the range where we live. 0 degrees Fahrenheit is really cold. Here's body temperature, 98.6. Up at the top, water boils. But we pretty much live here. But we have to come all the way down to here for liquid nitrogen. Liquid nitrogen, minus 320 degrees Fahrenheit, 77 Kelvin. That's 77 degrees Celsius above absolute zero. Liquid nitrogen is closer to absolute zero by far than it is to where we live. So this is 2/3 to 3/4 of the way to absolute zero. This is really cold stuff. So the question then is, what would happen if Perry put his finger in the liquid nitrogen? Now, Perry, unfortunately,
I'm not volunteering.
is not volunteering. However, we have flowers that have volunteered to do this. So Perry, if you want to take 2 of the flowers.
All right. Let's get them nice and cold now.
You can hear the boiling. The flowers are really hot. They're 300 degrees hotter than the boiling point of liquid nitrogen, making the nitrogen boil. When the boiling sound stops, then we know the flowers are at liquid nitrogen temperature.
Almost there. I'll give one to you.
Looks fine, doesn't it?
All right. Brush it. There's
Yeah.
All right.
But it's very brittle. If I took a regular flour and I crushed it like that, it would be fine. This one, frozen. So the next thing we can look at is what happens if I put a match in liquid nitrogen. Now, there are a few different things that the match could do. The match could burn brighter. The match could not burn as much. Nope, just leave it.
That's
I'm
good.
All right. Match could just stay the same. It could go out or it could explode. So which of those do you think the match is going to do? Here's my match. Just in case it explodes, I'll be down here. And you notice that the match went out. Why did it do that? Well, I didn't put it in the liquid nitrogen. The level of the liquid nitrogen is down around here. The match only went into about here. I can put my hand in here. No problem. It's like reaching into the oven to get cookies. Air is a very poor conductor of heat, so you can reach in and put your hand in the oven. As long as you don't touch any of the metal bits, you're fine. So let's take a look. The way we'll take a look now is I'm going to put some more liquid nitrogen in this cup. And then, Terry, while I'm doing this, if you would refill the dewar, please. And you can see that liquid nitrogen is boiling away. We've got a couple carnation petals in there. Here's another match. What I can do, this cup is full mostly of cold nitrogen. So if I pour it out onto the match goes out. So the match went out not because it was so cold, but because there was no air. And all the liquid nitrogen that was in the dewar that was boiling furiously was turning into cold gaseous nitrogen. And so the dewar is full of liquid nitrogen in the bottom the top 3/4 was gaseous nitrogen. Flame needs oxygen. There was no oxygen. Same thing here. Liquid nitrogen in the bottom, gaseous nitrogen in the top, and I can pour it out. And that fog, the water vapor, shows us where the liquid nitrogen, or where the gaseous nitrogen is flowing. Now, one of the things we're going to want to look at is how different materials behave when they're cold. So I've got a racquetball. I've got a ping pong ball, and I've got a super ball. The next thing I have is I have a pewter cup here that I can hold it by the handle, and it's pewter, so it's a beautiful bell, right? Clunk, clunk, clunk. Okay, it's not a very beautiful bell. Maybe we can change that. So we'll put the pewter cup in the liquid nitrogen, and we're putting them in now to give them time to get cold. And again, liquid nitrogen evaporates really quickly, and all this fog here is the same fog you see in a cold day when your breath condenses.
All right. So we're going to give those objects a couple of minutes to cool off, start getting down to that cold temperature. In the meantime, let's bring back to our concepts of what's happening to pressure. Like when I say I've got a balloon. What happens to the balloon when I introduce it to the liquid nitrogen? What's going to happen? All right. Go ahead and bring it in. The air inside the balloon is getting cold. Oop. Cold air reduces the pressure. As soon as I pull it up, you can see it start to expand again. It's starting to come back to room temperature. Come on.
Okay, now put it in and leave it in.
Now we'll just...
Let's see what happens when it gets really cold. So you notice that as it gets colder, the air's volume's decreasing, the pressure's decreasing, it's getting smaller and smaller. Just let go. Just let go. Yep, just let it go.
Sorry.
And the other thing is that, well, this is liquid nitrogen. The air in the balloon is oxygen and nitrogen. The oxygen is liquefying. The nitrogen is also liquefying. So, in fact, there's just a puddle of liquid air at the bottom of this balloon. But as it warms up, it becomes gaseous again, and it expands, and looks like it's doing okay. And in fact, if I heat it up with my hand, then it's going to expand even faster. You notice I'm heating it up with my gloved hand. Need to be careful here. Now, one of the things that happens is that, we put the balloon in the liquid nitrogen, it got really small, it got really cold, we warmed it up again, it's fine. We put the flour in the liquid nitrogen, and you can see that this flour was never in liquid nitrogen. This flour, which was frozen and warmed up again, it's warm now, doesn't shatter, but it's looking pretty darn sad. So if you had any thoughts of immortality, having yourself frozen in liquid nitrogen in order to be revived later, you'll come back like this really sad flower if you're not very careful. The reason for that is the cells in the flower, the cells in our body, have cell membranes and cell walls. When it freezes, it makes ice crystals, breaks the cell walls, breaks the cell membranes, turns the cells into mush, and no, they're probably not going to be able to revive you 100 years from now to cure whatever ailed you. Okay, so.
Going back to, we saw when we chilled the balloon, how it collapsed. Let's see what happens when we let that liquid nitrogen, thank you, when we let the liquid nitrogen sit in a closed container. Oop, don't want the ping pong ball. Keep getting it.
More than that.
Yeah, I mean, little. You can see how it's constantly expanding outwards. That gas, as it's evaporating, is pushing out. So now we're going to seal it. So what happened? I trapped the gas. The gas inside is constantly evaporating. The pressure is building up inside the soda bottle until finally the seal breaks and it pops.
And so the other point to make is what makes an explosion is not the expanding gases, but the fact that they're confined. So when I just put liquid nitrogen in this cup, it boiled away, no problem. But if I put liquid nitrogen in this bottle and seal it, then the pressure is going to build up until it releases somehow, and depending on how tightly it's sealed, that can be a really big boom. Liquid nitrogen, yeah, we'll just dump some out. So, what we have then is we have a few balls, and okay, we've got the racquetball, deal that later. Put that back. Ping pong ball. What happens to a really cold ping pong ball? Does it bounce higher? Does it bounce lower? Does it shatter? Well, it's a ping pong ball. It's basically just like it was before. No problem. Let's take a look at ball in here, in a super ball in here somewhere. Okay, super ball. Is it going to bounce higher, bounce lower, or shatter? Well, super ball is not bouncing. So the super ball became a lot less elastic. Last, let's take a look at the racquetball. So, racquetball, going to bounce higher, lower. There, it just bounces, doesn't bounce, but what will happen is if it hits something hard enough, it shatters. Carpet that I hit it on the first time wasn't. And then, last of all, we've got the pewter cup, which, remember, it gave off such a lovely thud last time. Now that it's been really cold, it's a nice bell.